Today, I'm going to discuss about Rankine cycle. Rankine cycle is a power cycle used in power generators, um, um, and also the medium of Rankine cycle is water, and also Rankine cycle basically based on thermodynamic first law of thermodynamics, where energy cannot be created, cannot be destroyed, and all we could do with the energy is convert from heat to work or work to heat, one of the two ways. So this is the first law of principle. So given that, um, what I have here is a PV diagram of water. So as you know, water can be in a liquid stage, also it can be in a vapor stage, and also it can be a solid state. When this is the critical point, at that point, all three phases are in equilibrium. And so this line, which I have here, is a saturated liquid. So all on the left-hand side would be saturated liquid. Then from triple point all the way down will be a saturated vapor point. That's what I wrote it down here. And then this side will be a vapor. And in between is a mixture of liquid and vapor. So now this is a PV diagram for the water. And then if you overlay Rankine cycle, basically you are having, you heat the water in the boiler, and there is a constant pressure, heat, and that turning into from liquid to the saturated vapor to the superheated vapor, which is steam, and that goes to the turbine. So if you come back here and look at it from boiler 1 to 2, you are heating it, and then this whatever the heated water is turned into steam is going to the turbine. So this is the turbine portion. So where is the turbine? In what happened in the turbine? Turbine, you're expanding the superheated steam to lower pressure. So from high pressure to the lower pressure. And so in that expansion, you're converting the steam to run your generator. So you're converting into work. And from there, it goes to when all the heat is taken out from the steam, most of it, and then it goes to the condenser where you are turning into saturated liquid. So that is the cycle. So 1, 2, 3, 4. So and then from here, now to go back, you are using a pump or some mechanism to increase the pressure. So when you're pumping a liquid with a into the system, then it builds up the pressure. So that is the cycle you're going through. Coming back to this schematic of the Rankine cycle. So turbine, you're expanding. We talked about boiler is heating the water, turning into steam, and from steam you're expanding it, is turning into the work here. So you could put down it's connected to the work. The work is generated, and then from here you're condensing it. And once you're liquid stage and you're running through a condenser is making sure all this vapors and everything are brought back to the liquid stage, and then you're going and using the pump to pump it back to the boiler. That is a typical diagram, the typical cycle of the Rankine. So when you are looking at this PV diagram, you could also generate a TS diagram. TS is temperature and entropy, where PV is pressure and volume. So in this case, what is happening is from 1 to 2 is boiler. That's how remember we talked about. You're heating the fluid and you're turning into the superheated steam. And so before it, just to give one point here is from as you're heating it, it turns into vapor, steam, and this is a saturated section of the line, and from saturated you're turning into superheated. So that is 2 dash to 2, and then you are going to the turbine, and it you're using taking that high power steam, converting it to work and to the expansion, and then go back to the. So you have both TS diagram. And so here, one thing added here is another portion pump. In a Rankine cycler, the one we are using, Rankine cycler is a kind of a small model of a power plant Rankine cycle. So in that case, we are not, we, we don't have any pump to pump back. So we manually put the water into the boiler and take it out. So that's the difference between Rankine cycler. So it's just like a model generated for um, experimental purposes in the lab. So this is not an actual map. So that is the mechanism we have. Let's go into the processes. What happens 1 to 2? 1 to 2 is a constant pressure heat addition. Why constant pressure? Look at this, 1 to 2, the pressure on this diagram is a straight line. So what happens in that one? Saturated water, which is a liquid water, is turned into saturated steam. And then from during 2' to 2, remember I told you about this 2' to 2, that area, steam is superheated. So we can calculate how much heat supplied by this equation. Qs is equal to H2 minus H1. H is enthalpy here, enthalpy at the point 2, enthalpy at point 1. So he's talking about point 2 and 1. So this is the difference between the enthalpies is what's going to give you the heat supply. So from there, we are at the already at 2. 2 to 3 is an asentropic expansion in turbine. So when I say asentropic expansion, that means a constant entropy. That here, if you come back here, if you look at it, is entropy on the x-axis, 2 to 3 constant, is straight line. So that's what asentropic expansion is. So what exactly happens in that one? Steam expands asentropically into steam turbine to the condenser. So you're feeding here, which is a high superheated steam, and you are going through the turbine blades, and it is expanding it. That means high pressure to low pressure, and then, but it is an isentropic process. It's a constant entropy process. So then also steam turbine develops a mechanical work. If you want to calculate mechanical work, this where you said is equal to H2 minus N3. That means you need to know the enthalpy at point number 2 and enthalpy number 0.3. So we got, so that's how you calculate. Now the last two processes left was process 3-4, which is condenser pressure heat rejection. I mean, it's not condenser pressure, it's a constant pressure heat rejection. So that is what we are going to be doing. Constant pressure heat rejection that's happening in the condenser. This is our condenser area, and that's where we are doing it. That means whatever the heat left after expansion in the turbine is rejected. Then to calculate that, you use this formula, heat rejected. Q in condenser is H3 minus H4. And the last process is isentropic compression. So from here, you're isentropically, you're compressing it from 1 to 2. In our Rankine cycler, we won't be doing that, and we just stop our work with the condensation process. But these are the main processes that takes place in the Rankine cycle. So the last one is pump work. If you want to calculate the amount of work that's done, H1 minus S4. So what is important here is to understand the 4 processes, and also if you look at it, 2 processes are constant pressure. For example, 1 to 2 is a constant pressure heat addition, and 3 to 4 is a constant pressure heat rejection. And then you have another process, process 2 to 3, asentropic expansion turbine, and then 4 to 1 is a asentropic compression in the pump. So there are 2 constant pressure processes, 2 constant, asentropic compression process. Both one is expansion, other one is a compression. So that summarizes the mechanism of a Rankine cycler, and so the important information you need to really understand is the PV diagram of the liquid water, but that's the liquid water we're using in the power plants. And then also the TS diagram. We should be able to remember how to draw the PV diagram and also the TS diagram, and it's just schematic of a Rankine cycler. So that concludes the explanation of the Rankine cycler.